So, kinetic molecular theory, or the dance of the molecules. So, kinetic molecular theory explains the behavior of gases, but it also explains the behavior of liquids and solids. What we could do is we could take what we know from the behavior of gases and then extrapolate that to the rest. And we'll show you what we mean about halfway through this class. So it describes how particles and gases move and interact. This theory helps us understand temperature, pressure, and volume specifically from gases, from what we observe of them anyway. Now I want you to think about it for a second. Can you think of examples where you've observed gas behavior in everyday life? And the reality is every single one of us has, because all of us deal with gases all the time. And I'm not just talking about that kind of gas. Well, these key principles of kinetic molecular theory can actually explain everything you would have observed in your reality. The first key principle of the kinetic molecular theory is that all matter, no matter what kind, no matter what state, is composed of tiny particles in constant motion, even if it's something as small as vibration. These particles have space between them, and it's the space that determines whether something is going to be a gas, a liquid, or a solid. Particles collide with each other and container walls elastically. Now, when we say something is elastic, we mean that they bounce back off each other. Okay, so it's not just a collision and then they stick together. It's collision and then bounce right back. Or you could see the reversal of momentum. The average kinetic energy of particles is proportional to the temperature. And the final part is, or a question I have to you, what do you think happens to particle motion as the temperature increases? Well, your motion is going to accelerate or it's going to increase. And if you think about it, if your seat is hot, what are you going to do? You're going to jump right out of it, right? Your movement is going to increase. Well, particles, no matter how small they are going to work the same way. Now, gas particles move in straight lines until they collide with other gas particles or the rims of a container. And what this means is because they're not merely attracted to anything else, they kind of just keep going in the direction that they originally sought from. And that's sort of Newton's first law of inertia, right? Where an object will want to remain in that motion until an outside force stops it. And so they have high kinetic energy and they move rapidly and constantly. Particles are far apart compared to their size, and the intermolecular forces between gas particles are negligible. In fact, what we usually say in chemistry is that there are no intermolecular forces. There's very little attraction between gas particles. So how might this behavior differ if we're comparing gases to liquids or solids? Well, starting from the right over here, we have a collection of solid particles or particles that have combined to make a solid. Then we got liquid, then gas, and then, of course, farthest on the right, we have charged distant gas particles, otherwise known as plasma. Now, in solids, you got particles that are tightly packed in a fixed arrangement, and they have the very least amount of kinetic energy. In fact, they kind of just vibrate up and down. Then liquids, the particles are closer together when we think relatively to solids, and they can flow, but they can't move in circular motion or or in several different directions at once, or any kind of rotational motion. And so they can take the shape of their container, but they still maintain what we would say a constant volume. And then you have gases, where the particles are far apart and they move freely. And these, if we're comparing to liquids and solids, they have the most amount of kinetic energy. And they expand until they fill the container and will try to move outside the container. Now, another thing that's going to come up when we talk about gas particles and collision theory is temperature. And with temperature, kind of goes in hand with kinetic energy, or the energy involved in movement. And so temperature is simply just a measure of the average kinetic energy of particles, so how rapidly they're moving. And as temperature increases, the particles will move faster. And as we remember from solutions, if the particles move faster, you have a greater chance of collisions. So this increases the frequency and the force of collisions. So if you can hit the particles at a higher speed, there is a greater chance that you'll have an inelastic collision. And so with this in mind, could we explain why a balloon might expand when heated? Well, that's because with heat comes increased movement, and if you can increase your movement of particles, then you can increase the distance between the particles, because the more you move, the more distance you can travel. And lastly, as particles move and strike the walls of the containers, you have what we call pressure, or a force that is applied over an area. Pressure results from particle collisions with container walls. Again, force applied by the particles over a certain area. More frequent or forceful collisions increase the pressure. Pressure is uniform throughout a container. And so one question I'll leave to you is, how do you think increasing the number of particles affects pressure? Well, if you got more particles that are confined to a space, then it is more likely that collisions with the container walls are going to occur. And if there's a higher frequency of collisions, then you're going to have higher pressure.